be a productive experience for all of you and help you guys do well on the test and get the score that you want. So if there's a concept that I've explained that you're not getting, let's go through it again. Okay, so now that everyone has gone in there, let's go to the next slide. Okay, so which of the following solvents is the most polar? So it's gonna show up on your phone and you're gonna go ahead and vote. Let me know what you guys think. Okay, we got a lot of votes for ethanol, a couple votes for methylene chloride. We still have a couple people. Okay, let us take a look. Okay, so the most polar is going to be ethanol, and that's because it has that alcohol group on it. Um, and then after that's going to be methylene chloride, and then following that is going to be hexanes. So hexanes is the least polar. It's essentially just like a big long carbon chain, and so it's not going to react very much with with polar things. It's not very soluble in water, things like that. So why are we talking about polarity? Why does polarity matter? It's because of TLC plates and columns. So I don't know if you guys remember, but TLC plates are like the little white guys that we run, and that actually stands for thin layer chromatography. So essentially, when you run those little white sheets of paper, you're actually running like a mini column, which I feel like when I realized helped me understand like how columns and how TLC plates work. So TLC plates are polar. They're lined with silica gel. And then we measure how much it runs by using a retention factor, which is usually abbreviated RF, and it's going to be a decimal point, right? So it's kind of like on a percentage scale. So it's either going to be 0, which is where we started it, where we spotted it, to 1, which is where the solvent runs into. And then you're going to see the range, and that's going to be like, oh, it ran 0.5, or it ran like 50% of my TLC plate. So, one important thing about TLC plates is that they do not determine purity. Okay, so if I'm running like a ton of TLC, say I run 4 different TLC plates with 4 different solvents, and one of my TLC plates shows 2 dots, one of them shows, another one shows 2 dots, another one shows 2 dots, and then the last one shows 1 dot. That does not mean that the one that showed 1 dot is pure. What it means is just like the way that my solution ran is different depending on which solvent I use, right? So we don't really use TLC plates to determine purity. More than anything, we're determining like the identity of things. I don't know if you guys remember when we did like the ferrocene lab, where you did like a bunch of the TLC plates and you were trying to figure out like where it was separated or not. Like TLC is great for that because I can see like, oh, I have my mono product in this fraction and I have both in this fraction and then I just have my di product. But it's not going to be helpful just determining purity. Something that would be good for that is like melting point, and then also like IR spec. But we have to take melting point with a grain of salt in Utah, right? Because altitude does affect it. So really quickly, decreasing the polarity of the solvent decreases the RF value. Can anyone unmute themselves and tell me why that is? Why does decreasing the polarity of the solvent decrease my RF value? Is anyone feeling brave?
Well, because the TLC plate is polar, it attracts the polar thing. So if the thing is less polar, then it will move less far on there. So it will have a smaller RF value.
Perfect. That is exactly right. So my TLC plate is polar, right? And so if my solvent is non-polar, then my solvent's going to interact more with my sample that I'm running. And so my sample can't move as far up the plate, right? So inversely, if my solvent is more polar, then my RF value will increase, right? Because my polar solvent will be interacting with my TLC plate a ton, and then my solution, my sample that I'm running is going to be able to go really far. Okay, so remember polarity. Also, I don't think I said this at the beginning. You guys are welcome to take pictures of my slides if you want to, if you want this cute little GIF with our polar bear dancing because we're talking about polarity. You're welcome to. But yeah, okay. let's move on. So this is another question. Let me pull up the QR code. So if you're not joined, you can join again.
Can I
How
ask
can
a
we
quick
improve the
question?
separation quality? Oh, yeah, Colton, what's your question?
Yeah, so the more, as far as what you dot on a TLC plate, the more
Mhm.
non-polar product that you have, that'll go farther? Or which one of those? Not the solvent, but what you actually dot on the TLC plate.
What you actually dot on the TLC plate. So it depends on what your solvent is that you run it with. So say we're running two samples. One of them is polar and one of them is non-polar. And we run them both with methylene chloride. The one that is polar um, generally moves more. Let me fact check myself there. But yes, so Kemi, she's locked in. I'm pretty sure the one that's polar generally moves more. Let me double check. Just 1 second. Sorry, TAs are human too. We don't have all the answers. I
I
just
do not
know
blame
where to
you.
find
Don't
them.
worry.
So let's take a look. Okay, so TLC plates are polar. So if I have a more polar thing, I think it will move farther. Is anyone disagreeing with me on that? No? Okay, cool.
Great, thank you.
Yes, absolutely. Okay, everyone get in. Oh, I like the Patrick meme. I didn't know you could add those. How can we improve the separation quality of a column? What do you guys think? They're just put in whatever. Oh, wait a second so you guys can type a longer column. I like it. Thanks, guys. Start with less polar, go to more polar, different solvents in different stages, distinct compounds. Okay, perfect. So let's talk through this for a second. So let's say that I'm running a column. So that'd be like the ferrocene one again that we did. And remember how we spotted a bunch of TLC plates, and the goal was to have a couple of fractions that just had one product, and then you probably had a couple of fractions that had both products, and then you want fractions that just have the second product, right? So let's say we're looking at that, we run our column, and it seems like a lot of my fractions have both of my products in it. So I didn't do a good job separating the two things that I made, right? So one thing that we can do is actually use a less polar solvent. So whoever said this one, you're doing amazing. That is correct. Um, so adding a less polar solvent is going to make it so whatever is non-polar will come out first. So it'll add like more separation between my two things, right? So let me just, I have an example on my phone I want to read through. Let me show you. So if I have two compounds and I'm running it with dichloromethane and hexanes at a 10-to-1 ratio, and it's not separating out, what we want to do is add more hexanes in that situation, right? Because my polar interacts with polar and my non-polar interacts with non-polar, right? So if I use more non-polar solvent, then that will run through first and my polar stuff will get stuck. And then, wait, did I say that right? Yeah. It'll get stuck in my silica gel or in like whatever's in my column. And then once that's run through and I see like a clear gap, then I can change my solvent to be something else, and then it will run it through. So if I'm trying to improve separation, changing my solvent is a good idea. Shaking it, probably not a great idea. You mix what you just tried to separate. A longer column would also work because then you could see like that separation more. Lots of fractions, also great idea because then if I have like a contaminated one, hopefully at some point I isolated one that is just that one product that I want. But yeah, I would say use a less polar solvent, probably like the best answer here. Okay. So I know this is everybody's favorite dietary topic and enantiomer topic. The deuterium test is honestly like the bane of my existence, but it's super important. There is a question on the test that's about this. So distereotopic is a different chemical environment. I like to think distereotopic, D different, so they both have Ds. So they're usually not always found on the same carbon. So it's going to be something where like I have an OH group that's a wedge, and then I'm comparing H's, and one of them is a wedge and one of them is a dash. And so because of stereochemistry, they end up not being in the same environment. So they're going to produce two separate signals on H and MR, and then when I'm doing the deuterium test, only one of the stereocenters will flip. So if I have R and S, if I do the deuterium test, it might switch to R and R. And then in antiotopic, they're the same. So, or like equivalent, you could think of. So an antiotopic equivalent. So they're usually, there's like a plane of symmetry. So I might have like a group here, and then I'm comparing the hydrogens here. Make sure to think about ketones as well. So like if I have a double bonded oxygen, that makes like a ring planar, or it makes like a chain, like a double bonded oxygen will sit in the chain. So then if I'm comparing hydrogens, those would be in the same environment. If I do the deuterium test on an antiotopic one, it's going to flip both stereocenters. So from R to R and S, it'll go to S and R. Um, if you struggle with this, I'd super recommend watching the reduction of a ketone lab at 1319. That's like the timestamp on the YouTube video. He goes through it and I feel like he explains it really well. So this is something you struggle with, highly recommend doing that because there is a question on the test that is about this. So let's move on. We're going to do a quick practice question. So oh, there's music. I don't know if you guys can hear that, but I can hear that. Um, let's let everyone join again. I put the QR code up. Looks like we have Isaiah. I know that there are at least 10 of you in my Zoom, so hopefully we can get some of you in so you can participate. Oh, I have 23 of you. Okay. You don't have to put your real name. I won't judge you. It's okay. But just don't put anything sussy, please. Thanks. Okay. Is everyone in who wants to be in? Okay. You get more points if you answer fast, just so you know. Okay, match the term to the image. So you're going to see two molecules and you need to decide if it's enantiotopic or distereotopic. Okay, you have 15 seconds left. Okay, that was really fast. So if you didn't get it, that's okay. But let's look at it really quick. So I'm pretty sure, can you guys see the molecules still on your phone? Do they show up? No?
Yes.
Yes. Okay, cool. Thank you, Jake. So if we look at the molecules, I don't know that it will let me pull them up on my. I'm pretty sure one is, so they're both, I don't even remember what I put on this slide. Let me pull it up really quick. Over. Do. So when we're looking at an antitopic and diastereotopic, it's really, I think for me, the first thing that I look for is a plane of symmetry, because if there's a plane of symmetry, that's a good indicator that it's going to be an antitopic. Okay, let me share this. Cool. So if we look at this molecule right here, we're comparing these two hydrogens on these sides. And so we have an alcohol group that's a wedge. And then if we look at it, we're comparing a hydrogen that's a wedge and a hydrogen that's a dash. And so what I like to think about, like sometimes if you're in my section, you've probably seen me do like a funny dance. But if my carbon chain is here and I have my oxygen here, if I have a hydrogen also facing forward, is that the same as a hydrogen facing back? Relative to my alcohol? And the answer is no, it's not, right? Because one of them is going to be closer, it's going to be in the same plane as the oxygen, and one of them is not. So if we look at the stereochem assignments here, we can see that it's SR and RR, and only one changed, which means that it's going to be diastereotopic. Perfect. So then if we look at the next one, I think I only gave you guys this one that's on the, oh, I don't know what I did. Okay. I think I only gave you guys the one that's on the left. So now we're comparing the one that's a wedge on the left and the one that's a wedge on the right. And if we look at the stereo center configurations, it's SR and then it goes RS, which means that both of them flipped, which means it's an enantiotopic. We can also tell that because there's a plane of symmetry down the molecule, which is a good indication. And then also I'm comparing a wedge to a wedge in relationship to a wedge, which is a lot of wedges. But if I'm thinking about two hydrogens that are facing forward and then also an alcohol that's facing forward, all of those are going to be affected the same because they're sitting in the same plane. So that's kind of how I work through it. Again, if you struggle with this, I'd super highly recommend going through, how do I close this? Going through the video that I linked in the video, the reduction of a ketone one, because that will be super helpful on the exam because you definitely have to do this. Okay. Here we go. Oh, we have a leaderboard. Good job, Tina, Isaiah, David. You guys did it really fast, so congratulations. Okay, so the next thing we're going to go through really fast is mass spec. So mass spec, I have to be honest, it's really dumb. It doesn't really show you very much, and we don't use it a ton in the class. The main thing that mass spec is going to tell you is the mass of the molecule. So we always have mass spec when we're doing like the identify a molecule. So it's kind of like the first thing that I will look at because it will give you the mass. So what we do is we're going to go to the group that's most right. So the group of peak that is most right, and then we're going to find the tallest peak in that group. So if we're looking at this one that I have on the slides, I'm not going to look at this peak that's at 99. That's actually going to be an isomer, I think is what it's called. It's going to be like a different version of what I have. So if I was looking at like carbon 12, it's going to be a carbon 13. And so it's a little bit special. The one I'm looking for is the really tall one at 98. And then just make sure that when you're looking at it, you double check the scale because sometimes the scales will change. So this one is really nice because each little dash right here on the bottom is 1. So my mass of this molecule right now is going to be 98. And then just so you know, on the bottom of the graph, it's actually a mass to charge ratio, but in this class, our charge is almost always 1. So my x-axis essentially ends up being my mass. So if you get to that, like deduce the molecule thing, look at this. The only thing you're going to get from this really is the mass. And then remember that if it's odd, that there's going to be a nitrogen in it. But anyway, just so you know. Okay, the next thing we're going to go through is IR spec. I would highly, highly, highly recommend taking a picture of this slide if you don't have a picture like this. Also, remember that the test is open note and open like lab notebook. So if when you do the IR specs, you frequently have like the labeling chart open or some other resource, make sure that you have that while you're taking the test because it is not open internet. So you can't look anything up while you're taking the test. So, but if you have a picture of this slide or you have a picture of another resource that helps you do IR spec, definitely make sure you have that when you take the test because it will just make your life easier. So some key things, carboxylic acids look like funnels. They're like really wide. They'll probably have an OH peak as well. But they're going to be like a big bulky group towards the left of your IR peak, right? So 2500, 3500. An aldehyde is going to have rat teeth. Some people call them daggers. Basically, it's two little points around 2700 and 2800. Benzene is going to be like that aromatic region that we saw in a ton of the labs. It's going to be like a lot of little spiky peaks towards like the middle of my IR spec. And then anhydride is a functional group. So it's like two ketones with an O in the middle. That confused a couple people. So if you don't know what a anhydride is, Google it. It's good to know what that is. And it's going to have a split peak at the carbonyl. So the carbonyl will look like it has 2 points. And then something that's really important, a lot of people miss this on the midterm because it's kind of unique. We don't see it very frequently, is sterically hindered groups are narrower. So for example, on the midterm, we saw an alcohol peak, but instead of being like that nice big like U shape that we normally see, it looked more like a V. And we worked through some of this on a post lab, but really what's important about this is, so like when I have a big alcohol peak, it's like hydrogen bonding and the bond length is shifting, which means that the bond length is variable, which is why I end up with that U shape, right? Because my IR is measuring like a bunch of different bond lengths. But if I have sterically hindered things, so when I think of sterically hindered things, I think of like a tert butyl group, right? Because that's really big. Then I'm not as able to like hydrogen bond with my OH. And so it's going to be smaller because there's going to be less variation in the length of the bond. So just remember, if I'm looking at something and there are big bulky groups around it, it's going to be a narrower peak. It's going to be more pointy. So just keep an eye out for that. Like alcohols, they're always going to be around like the 3200 range, 3600, but they might be pointier than you expect if they're surrounded by big groups. Okay, so we're gonna do another practice question really fast. So we're gonna do some IR characteristics. So everyone get your phones out. Hopefully it's not too fast timed. Oh, you have 45 seconds. Okay, so there are 4 different groups that I just talked about. One of them I did not read, so I'm sorry. Hopefully you know it. And then you're just gonna match it to its characteristic. Okay, you guys have 10 seconds. Sorry, I know it's really fast. Time is up. Okay, perfect. So 10 of you got it right. I'm assuming the person that didn't, you were rushing, and so I'm sorry. But yeah, so the carboxylic acid is that funnel shape we talked about. Nitro group is going to be 2 strong peaks. And these shifts are really important. If you're looking at an IR spec on the test, it's going to be right where like the help key says it will be. So if you're looking at something and it has 2 strong peaks, but they're not at 1550 and 1350, it's probably not a nitro group. Okay. It's kind of easy to confuse the nitro group and the ester because the ester will also have 2 peaks. So just really make sure that you're looking at like the shift on it and you're making sure it's at the right number. So a nitro group will not have a carbonyl peak, but an ester will. Okay. And then an ester is going to have a CO bond peak, which is like around 1,000, maybe 1,100. But the nitro group peaks are going to be a little bit more left than that. So just make sure that you guys are paying attention to that. I might take a picture of these slides or this slide because those are pretty important functional groups if you catch my drift. So I'll give everyone a second to take a picture of that if you guys want. Anyway, so I would just review that. Whoever's doing the goat, I really enjoy that. Okay, cool. So leaderboard, you guys are shifting around. We got Tina, Porter, Elle, Megan. You guys are all moving up in the world. Welcome. Okay, so we're gonna talk about HNMR now. I know I'm going through things pretty quickly. Most of these things I feel like you guys have practiced a lot, but again, if you have questions, let me know. HNMR, the strat. Okay, you gotta look at integration. Please, 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 please look at it. Integration on this one. It's gonna be super important. It's gonna be really helpful. Splitting. Apparently it's so important I put it twice. One of those is supposed to say shift. So splitting and shift, and then resonance and induction. So if you're in my class and you ask me about an HNMR and it had a ring, probably the first thing I asked you is have you drawn a resonance structure. which is really annoying and I'm sorry, but looking at where partial positive charges or partial negative charges is really helpful. And then don't forget about doublets of doublets. So if I have a double bond, it's possible that I'm gonna end up seeing a doublet of doublets, which is gonna be one H that's gonna show up as like four peaks. Okay. And so that's an important functional group to look at and to understand. Um, so we're gonna work through this HNMR. It's from one of your homeworks. So in theory, you've already worked through it. But the molecule is right here. So I'm just gonna give you guys some time, maybe like 5 minutes or so, to work through this HNMR and just kind of think about how you would assign the peaks, where the peaks would go. Really quick, this 3 is in the middle here because this is one peak right here. So when you're assigning peaks, just pay attention to that. So I'm just going to give you 5 minutes, take a look, give it a try, and then we'll work through it together, okay? Okay, guys, I am back. Here, I guess I'll show you my lovely face, even though I really hope none of you are watching my lovely face. Okay. Hopefully you guys had a chance to work through this. Let me put it on a little low. Okay. So this is kind of my strat when I was going through it. So I made this lovely little table. And so if I'm looking at A, why is A a doublet? What was I smoking? So A is going to be integration of 1. We're going to ignore that splitting column for a second. I don't know what I was thinking. And then it's going to have a partial positive charge, right? Because of the oxygen. So then if I look at this, I don't think this is right, actually. Completely ignore that. Let's go to the next part. So hopefully you guys all looked at, here, let me pull this up again. Yeah, so hopefully you guys all looked at the molecule, we're able to work through it, and then I can go back to that slide and we can look at it. But my table was wrong, so we're gonna ignore that. So what it's gonna have you do is order the hydrogens from left to right. So it should correspond to the peaks that you had, right? So peak 1 is gonna be the most left, and peak, I think it's 7, is gonna be the most right. And just give it a shot, and then we'll talk through it, okay? And I, in the meantime, is going to find that problem and find the key for it. Thank you to the 6 of you who have answered your real ones. Oh, now 8. Good job. Just give it a shot. We'll work through it, I promise. I just want to make sure that I'm not leading you astray because I messed up the H and M R on my first review and I feel bad. Okay, 10 of you, good job. Perfect. Okay. Let's take a look at it. So one of you got it right. Shout out to that person. So it's going to go A, O, C, M, P, solvent, and then B, which is really weird. So let's go back and take a look. Okay, so this might actually be right. So let's take a look. So if I'm looking at this molecule right here, this is actually the cinnamaldehyde lab that you guys did. So this is the steam distillation one. So if I'm looking at, let me find the key actually. Okay, so if I'm looking at this, if I draw a resonance structure, A can actually have a double bond, so it is a doublet. And so A is going to be a doublet, and then it's going to have a partial positive charge. And then if I look through here, C and B are on a double bond, right? And so if I draw a resonance structure, the bond will flip to be A, right? So then B is going to be split by both C and A, which makes it a doublet of doublets. So that is super key. One of the most important things about why I did this example is knowing what a doublet of doublets looks like. C is just split by B, so it's going to be a doublet. And then O, M, and P are going to follow their normal pattern. So O is going to be a doublet, M is going to be a triplet, and P is going to be a triplet. Okay. So when I'm looking at this, the first thing that I would do is probably try to find O, M, and P because those are ones that I've seen a lot, and I kind of know what they look like. So one thing that is annoying about HNMRs is that they don't always follow the patterns that we think they will. So for example, OM and P are going to be 2, 4, and 5 in this example, which means I have a peak in the middle. Don't worry about that. That's totally fine. That happens a lot in science where we think it's going to look one way and it's going to look a different way. So, say for example, I have a trans and a cis thing. If I end up with peaks in the middle, but I know that those are trans and cis, trust your gut, okay? Go by the shape. So, the first one I'm going to assign is O. So, O is going to be 2. And I can tell that partially because of the integration. So, you can see the integration here is a lot taller than, say, like for 3 or over here for 5. It's just like that short jog. So O is going to go right here on my 2 peak. And then I'm going to go over here and it'll be like, okay, where are M and P? So I always distinguish M and P. They're going to both be triplets, which in this one they don't look like triplets, but on the test it will be really obvious. Um, their P is always going to be shorter. And usually it will be shorter like in the peak, but it will also be a shorter integration. So if we look at this integration right here, we can tell that that's about double what this integration is here. So M is going to be 4 and then P is going to be 5. Okay, so we have O, M, and P assigned. So that leaves us A, B, and C. And then our solvent is 6 right here before I forget. So that like that little baby peak. And we can tell that as a solvent because one, it's where solvents always are. And number 2 is it doesn't have an integration on it. Okay. So we're now looking at A, B, C, and we have 1, 3, and 7 left. And so we have to decide where those are going to go. So first thing I would do is look at proximity to like a functional group. And so A is closest to a functional group, meaning it's on an aldehyde, it's close to a carbonyl, which is an electron withdrawing group. And if my electrons are my shield and I'm by an electron withdrawing group, that means I have less shield. I'm going to be de-shielded, which means I'm going to be left. So my A is going to be over here on 1. And then that leaves me with C and B. Okay, so C and B are kind of the trickier ones to find, but I don't know if you guys remember, I said when we drew a resonance structure, B ends up being split by both C and A because of the resonance structure moving the bond. So my B is going to show up as a doublet of doublets, and my C is going to be just a doublet. So if I look at between 3 and 7, I can tell that 7 is a doublet of doublets, and so that's going to be B, and 3 is just a doublet, and so that's going to be C. So I know I worked through that really fast. Let me just switch to the key slide. Oh, here, do you guys want to see the leaderboard? Porter has a streak. That's pretty cool. Okay. So this is the answer key, right? So I see A, O, C, P, M, and then CHCl3 and B. So a couple key takeaways. What does a doublet of doublets look like? It's going to be 4 peaks really close together, but you're going to see that the integration goes up about 2 hydrogens, okay? Another key thing is OM and P are usually together in where we see it, but sometimes we end up with a rando peak in the middle. That's okay. Okay, trust the science, trust the process. Let's see what else. Cis and trans hydrogens are super important. Hypothetically, if I had a double bond on an end of my molecule, I would end up with 3 hydrogens that I'm talking about, right? Because I would have 2 hydrogens on the end and then my hydrogen in the middle. Think about like what would happen there, right? So one of my hydrogens is going to be split by both of them, and then the other ones are only going to be split by one other hydrogen. My slides just died. Just a second. So just review what a doublet of doublets looks like. Review cis and trans, how they show up. I don't think you have to calculate the cis and trans coupling constants, just so you know. But it is good to understand that trans are usually more downshielded than cis are. My laptop just turned completely black, so just give me a second. I'm going to stop sharing and see if I can troubleshoot it. So sorry about that. I swear I am not technologically inept. I've never had this happen before. Apparently, my interactive presentation is just too much for it. While I'm pulling this back up, does anyone have any questions about IR spec, about HNMR, or any of the other things we've talked about?
So you said trans across a double bond will be more de-shielded and more to the left.
Yes.
Okay.
So a trans peak is usually going to be more de-shielded, just so you know. But I would also like you gotta draw a resonance structure because if you end up with like a partial positive charge somewhere else, that's gonna take precedent. Okay. So, but that's just like a general trend that I have seen. And then just review what a doublet of doublets looks like. Because that will be really important. And also like leaning might be helpful. Um, anyway, there may or may not be a double bond in the one you have to do on the test. Crazy.
Crazy.
Okay. Does anyone else have questions? I have rescued my slides. Maybe. If this one was hard, he does walk through it on the steam distillation video at 10:47, so you can go through and look at how he did it. That can be kind of helpful. Just remember what a doublet of doublets look like. And remember, like, trust the science. If things end up in the middle of things, that's okay. And cis and trans do not have to be right next to each other. So maybe my cis is over here, my trans is over there. That's totally fine. It'll be okay. Okay. Het core. You've done a bunch of het core. Het core is like that one graph that will show up on your CNMRs where it does like it plots like CNMR versus HNMR. I'm not going to go through that because I think most of you understand it. But if you are concerned about it, go and watch the NMR review video. So if you go on Learning Suite, you go to content, how-to videos, there's an NMR review. And then if you go to 2152, it will explain how to do that. But basically, I always do my HNMR first, and then I will compare my HNMR down to my carbons, and it will help me assign them because some of my carbons won't have any H's on them, and that will help me identify them. Or some of them I can correspond like, oh, this is A and this is C1, and so those go together. So I'd recommend just taking a glance at that video. If you want to take a picture so you don't lose the timestamp, you can do that. But I would just review het core. Most of you are pretty confident with it because most of the CNMRs we did this semester use het core, but just in case that is het core. Okay, so another concept that's really important is melting point depression. So if I have two compounds that have a similar melting point and I'm trying to determine if I have the two compounds or not. So it's kind of like, say I like get a white powder and I'm like, is this pure? Is it not pure? Is it two things? Is it one thing? I'm not sure. If I put two things that have a similar melting point both in my capillary tube and measure the melting point, it should go down. So this will tell us that they're different. So say I have two white powders and I'm like, are they the same? Are they different? I guess maybe white powders are a little bit sus, but that's okay. That's what we work with all the time. So you have two white powders and you're like, are they the same? Are they different? We're not sure. Whoever just reacted to that, that was really funny. Anyway, um, if I put them in, so I would measure them both first. So say I get a melting point of like 132 and 133, so it's really similar. If I measure them together, it would probably be like 120, maybe even 115. And that's a good indication that I have two things. Okay. So this is a really important concept. We've seen it. It's also something that we could use to determine purity, right? So if like my melting point is lower than I expected, I might have some contamination in my tube. I might have something else in there. So that's just important to know. If I have two compounds, similar melting points, my melting point is going to go down. Cool. Okay, solubility. We have not talked about solubility a ton in this class, but there is actually a question about it. Basically, long carbon chains are not very soluble, and OH groups are. So you want to think about the properties of water. What would interact with water? What would water be happy with? Water would be really happy with some alcohol groups. Super long carbon chain, water's not really vibing with that. It's not going to want to come out of solution, right? Because water has a bunch of OH groups. There's like polarity on that. It's going to react with ions, like ions will be soluble, but like a really long carbon chain won't be. So when I say look at the carbon to functional group ratio, if hypothetically I had to compare a bunch of molecules and one has two functional groups and one has three, and the one who has three has like a bunch of oxygens or like hydrogen bonding groups, the one that has three will be more soluble in water, okay? Um, quick thing, like carboxylic acids are pretty soluble in water, right? Because they can hydrogen bond, they have like that, depending on the pH, like you can have like an O minus and it will do like fancy chemistry things. So like carboxylic acids are good, OH groups are good. A benzene ring is better than a long carbon chain, right? Because a benzene ring is more compact, so it's going to be more soluble in water. Just heads up, I would review maybe like some solubility rules, but it's pretty simple. Don't overthink it. I think if people miss this, they're probably overthinking it. So don't worry. Okay, this is like a really stupid question. I have to be really honest. I don't know why it's on there, but there's a toxicity question. I'm sitting with my friend who took it with me and she's laughing because she knows which question I'm talking about. We've never talked about this in class. It's not talked about in any of the videos, but it's on the final. So good job for you for all coming to the TA review because now you're gonna know how to do it because it's honestly not hard, but it looks overwhelming. So we're gonna have a toxicity question and it's gonna ask you like which of the following is the most toxic or something like that. It's gonna give you a chart that looks overwhelming like this information and you're gonna be like, what the freak do I do? Okay. You're gonna look at the LD50 or the LC50 values. This is the medial lethal dose. Okay. So it's how much do I need to give whatever I'm testing on. So you can see we have man, we have rat, we have rabbit. I don't know what other things we have. I think that we have maybe like a monkey in here. So whatever like population I'm testing, how much do I need to give it? So like half of the population dies, which is like a really terrible indication, but that's what it is. So a lower number indicates higher toxicity, which if you think about it makes sense, but a lot of people trip this up. Okay? Because the less I need to give it for half of the population to die, the more toxic it is, right? Because if someone just, I don't know, so let's look at an example. So I'm looking at the toxicity data of acetone, and I'm looking, let's say, at which ones do I have in all columns? Okay, well, I should explain this first. Okay, so when I say compare apples to apples, well, you're gonna want to find a lane or like a test that's the same route of administration and the same species. So, for example, for ethanol, I have like an oral route human LD50. Oh wait, that's LDLO. Let's see. Um, okay. So I have an oral MUS. I don't know what that is. Probably maybe a muskrat. I don't know. We'll just say that. LD50 oral for ethanol is going to be 3450 milligrams per kilogram. Okay. So I'm looking at this right here. Can you guys see my cursor? Hopefully, yes, because I'm explaining based on that. And then if we go over to methanol and we're looking at that same classification, so oral MUS LD50, it's 73,000 or 7,300 milligrams per kilogram. Okay, so someone unmute, tell me between these two, MUS is mouse, my friend is telling me. Sorry, mouse. Um, which is more toxic, ethanol at 3450 or methanol at 7,300? Someone unmute, someone be brave. What do you guys think? The lower number is higher toxicity. Okay, cool. I will just tell you because I understand that this is new. So if we're comparing the mouse oral LD50 is 3450, and I'm comparing the mouse oral 7,300 milligrams per kilogram, ethanol is going to be more toxic than methanol. And I know that because 3450 is a smaller number than 7,300. Okay. So this question looks overwhelming, but it's really not that hard. All you have to do is compare the columns, find something that's in common in all of them, and find the smallest number, okay? the smallest number is going to be the most toxic. So let's do another example. So if I do oral route, oh wait, those aren't LD50s. Let's see. If I do inhalation route for the mouse, and I'm looking at an LC50, that's fine. So it's 64,000, okay? If I look at oral route for the mouse and I look at LC50 here, it's 52, okay? Which one is more toxic? 52, 64,000.
52.
52, exactly. Thank you. Okay, so keys here. Smaller number, higher toxicity, compare apples to apples. Okay, so when I say that, what do I mean? I'm saying it again and again because I really want you guys to get this question because it's not that hard. But just make sure that you're comparing, look for an LC or an LD50. Make sure you're comparing the same route of administration and the same organism, right? So you wouldn't want to compare the rat to the man, okay? Because rats and humans are different species. They're not gonna be affected the same way by, let's see, by a certain companion or a certain compound, okay? Um, Okay, so someone in the chat said, when you compare across lanes, do we have to compare LC50 to LC50 or can you do LC50 to LD50? I would do LD50 to LD50, okay? Do exactly the same thing, okay? So if I have an LC50 in one lane, find the LC50 in the other lane, okay? And if you can't find that, find something else, okay? Um, is that making sense to anyone? Does anyone have questions? Because this is definitely a question on the test, and I know that it's weird because we haven't seen it before.
So is it gonna be more like, oh, orally, which one is more toxic to rats? Or is it gonna be like, in general, which one of these is more toxic? And then we just choose our own organism and choose our own route of infection and
But
then compare them.
yeah, that's a great question. I'm pretty sure it's which of the following molecules is more toxic, like generally. And so what you're gonna do is you're just gonna find one route of administration and one organism and compare it, and it should tell you the answer. Let me just see if I have a picture of it and I can confirm that for you, but I think that's what it is. Which is why I'm saying it's really important to compare apples to apples because you want to make sure that you're comparing the right thing. Yeah. So it's going to be like, which of the following is more toxic or rank the toxicity of these molecules? And so it's going to be like, compare acetone to methanol or compare ethanol to methanol. And then you're just going to go through and look at it. And then I would just also double check that your units are the same. So if you're comparing milligrams per kilogram, make sure that you're comparing milligrams to compare or to kilograms in the other one. Okay, any other questions with this one? You don't even have to know what these things stand for. As long as you're comparing the same things, that's totally fine. Like if I don't know what IVN is, I don't know that's intravenous, that's totally fine. Okay? Just make sure you're comparing the same things. Okay? Any questions? Okay. Don't overthink it. It's really not that hard. It's just a little bit intimidating if you haven't seen it before. Again, lower number, higher toxicity, right? Because you ingest less and still die. Okay? So, a little bit morbid, but that's what it is. Cool. Moving on. Okay, everybody's favorite, extraction. Extraction is pretty tricky for a lot of people because if you make a mistake in the words early on, it can waterfall and you can miss a lot of points. So just say as you work through it, like fill all the blanks in and then go through and read it again and make sure that it makes sense, okay? And if you're filling it out and you get to a blank and you're not sure what should be there, um, continue reading because it might explain it, right? So say I'm like, I removed this layer after neutralizing it. After neutralizing it is going to tell you that it's either like a base or an acid, right? Because my organic layer, I'm not going to neutralize. So quick tips. If I add base to an organic layer, it's going to move the acid to an aqueous layer. Why does it do that? Because a base will deprotonate the acid, so my acid is now charged. It's in the aqueous layer because charged things are in the aqueous layer. If I add acid to an organic layer, it's going to move the base to the aqueous layer because now I'm protonating my base. My base will have a positive charge, and my charged things end up in an aqueous layer. Okay. So once I extract something, so say I have my base and it's protonated, it's in the aqueous layer, I'm going to have to neutralize it, right? Because I want to restore everything to the state that it was. So then I'm going to add base to then deprotonate my base. So then it ends up being neutral. Okay. I would take a picture of this slide. It's pretty helpful to just have like these tips when I'm going through. And then we're going to work through a practice problem. This is pretty similar to what you're going to see on the test. It has 3 molecules. So kind of like the H&MR, I'm going to give you guys some time, and then it's going to have another question where it's going to ask you like which blank goes with which letter option. Um, so I'm going to give you guys about 5 minutes to work through this. I really encourage you to work through it by yourself. I will go through it, but sometimes making mistakes and practicing thinking can be really helpful. So I'm going to give you 5 minutes, start working through it, do your absolute best. If you're not sure on a blank, just guess and go to the next one because you have 7 chances, okay? So I'll give you 5 minutes starting now. Okie dokie. I'm gonna switch to the question now. So you guys, if you have your answers like written down or you have like your thought process, you can go ahead and enter in what your responses were. I'll give everyone a second to get back in. Because I know that we're in college, but sometimes you really just need some points like Kahoot. But I couldn't do a Kahoot because I actually had to cover content. So it's a great value Kahoot. Okay. It seems like we have the people we're gonna have. Okay. So it's gonna have you rank, I think it's rank or match. Let's see. Yeah, so it's gonna have you rank them. So the first one is gonna be blank one, and then two, three, four, five, and so on. Okay, so you're gonna rate them in like order of how they come through the paragraph. And then if anyone else wants to join, the QR code is up and I think you can still join. Seven of you have your answers in. Good job. You're doing good. Okay, you have 30 seconds left if you still want to do the question. So it's just gonna have you rank them again in order. So the top one or the first one is gonna be whatever, like blank one, and then so on and so forth. I'm assuming you can count from one to seven in order. Hopefully that's not too bold of an assumption. Okay, 5 seconds left. Okay. Perfect. So four of you got it right. Eight of you didn't. That's okay. Um, let's walk through this. So here's the answer key. So let us read it through. You are given three compounds to separate. 1,3-dichlorobenzene, 3,5-dimethylaniline, and butyric acid. Right there, I'm going to stop. Okay. The first thing that I'm going to do is assign my base, acid, and neutral. Okay. Because those are the three things that I'm trying to separate. And I need to know the identity of everything so that I know what's going to happen when I add certain things. Okay. So butyric acid is the easiest one to find. It's the acid. Aniline is going to be my base because aniline is a nitrogen group. And so if I have nitros, those are general, or nitrogens, sorry, those are generally basic groups. We've taken OChem, NH3 is like more of an, anyway. And then 1,3-dichlorobenzene is going to be my neutral. Okay, so then I keep reading. Dissolve the mixture in blank in a beaker. So the first thing that I do when I have all of my compounds, I'm going to have them probably like in powder form, or maybe like a couple of them are in liquid or whatever. I want to put them all in an organic layer, right? Which is what we do in class, right? The first thing I do is probably add a bunch of either dimethyl or diethyl ether or dichloromethane, right? And so I would say I'm going to dissolve it in an organic solvent. So the first thing I'm going to do is dissolve it in an organic solvent. What are my two organic solvents? Dichloromethane and diethyl ether. Okay, so I'm going to look at my options down here. Methanol. Did we ever use methanol to dissolve something? No. Okay. Ethyl ether could be that one. I did use that. Did I ever use acetone in an extraction? No, none of you put acetone, okay? I don't want to see any acetone answers on any of yours, okay? We do not use acetone in extractions, okay? So NaOH, HCl, and then my products. Obviously, I'm not going to suspend it in my products. That would be kind of pointless. Okay, so ethyl ether or diethyl ether, they're the same thing, fun fact. So I'm going to dissolve my mixture in my organic solvent, diethyl ether. Is diethyl ether more or less dense than water? Somebody unmute themselves and tell me. Is diethyl ether more or less dense than water?
Less dense.
It's less dense. Thank you, Carson. So that means my my aqueous layer is going to be on top, and diethyl ether is less dense than water, so my organic layer is going to be on top, and my aqueous layer is going to be on bottom. Okay. If I had methylene chloride is more dense than water. So methylene chloride is going to be on the bottom, which is my organic layer, and my aqueous layer will be on the top. Okay. So it's really important that we understand that difference. So diethyl ether, less dense, it's going to be on the top. Methylene chloride, more dense on the bottom. Okay. Okay, continuing reading. Once dissolved, add 3 NaOH to create a bilayer. Okay. So what did I just add? I added a base, right? So if we go back to my fun little hacks that I gave you, if I add a base to an organic layer, what am I gonna do? I'm gonna move my acid to my aqueous layer. So we're going back here. So I'm gonna add NaOH and I'm gonna remove my acid. So I isolate my butyric acid. Okay, and so then by removing the blank layer, and I'm going to remove the bottom layer because that's my aqueous layer, and diethyl ether is less dense than water. So my organic layer is on top and my aqueous layer is on bottom. Okay, so that gives us 3 blanks. So I'm going to isolate my acid, and it's going to be in the bottom layer because I'm using diethyl ether, which is less dense than water. Okay. Once I've recrystallized that, I'm going to take an IR and I'm going to add blank to reform the bilayer in my original organic layer. So right now I have an organic layer chilling with a base in it and my neutral in it. So if we go back again to this slide, how do I get my base out of my organic layer? I add an acid, right? So I'm adding an acid, which is going to protonate my base. It's going to move it to the aqueous layer. There's on the bottom. And it's going to reform the bilayer, right? So I'm going to have an aqueous and organic layer, and then I'm going to isolate blank after neutralizing the aqueous layer with blank, okay? So this is one of those situations where you kind of have to read ahead to know what this space is going to be, because I could either isolate my aqueous or my organic layer, right? But I know that I'm going to isolate my aqueous layer because I have to neutralize it, right? So that means I'm going to take my base out because that's what's in my aqueous layer, and I'm going to neutralize it with base, right? Because my base is my 3,5-dimethyl aniline is sitting protonated, right, in my aqueous layer. And so if I add a base to it, it's going to deprotonate it and restore it to its original state. Okay. So we're working through, we have separated our acid and we've separated our base. So then we're going to put it through vacuum filtration, recrystallize, use your Hirsch funnel. I know you guys love it. And then my original organic layer is still chilling in my diethyl ether. So what do we normally do with our organic layer? We're going to dry it with sodium sulfate, which is going to take out any aqueous or like water layer that we didn't get out, evaporate it, and then we will have 1,3-dichlorobenzene, which is my neutral. Okay. Does anyone have any questions about that or how I worked through that? Yes, no, maybe so. I'm thinking no. Okay. So, oh, Jake?
Yeah, I was just gonna ask, is it gonna on the test, are we gonna have a neutral acid and a base that we are separating out? It will be those 3 for sure. Okay.
Mm-hmm. Yeah, it's gonna be 3. And it's always gonna be a neutral acid and a base, right? Because well, Technically, you could separate two things that are the same. So like if I had two bases, I could separate them, but it's a lot harder because you have to know like the pKa's and the pHs and everything. So in this class, you're always going to have a neutral acid and base because they're going to all behave really differently, and it allows you to isolate them fairly simply. I will say if you struggle with this, go and review the Cannizzaro lab. It's pretty helpful. And also maybe just make yourself a generic flow chart. Where you start with A, B, and N all in a beaker, and then you add base, and then what happens. Because if you have that generic flow chart, it's gonna hold true for any extraction that you do. And it's always the same. So, for example, on this one, if I ended up adding, instead of NaOH here, I added HCl, that's gonna pull my base out. So instead of isolating my butyric acid, I would isolate my base. And so this question tricks people up sometimes, but honestly, if you learn the patterns, which are in this slide, it will help you a ton. And if you're nervous about it, I'd recommend drawing out like that, like a simple, like generic one with just like acid, base, neutral. You don't even have to name the molecule. It's just like those three things. And think about, okay, if I add an acid to this, what's going to happen? If I add a base to this, what's going to happen? How would I separate it? How would I neutralize it? Because if you have that workflow, then when you get to the test, as long as you can identify which one is which, you'll have your workflow and you'll know how to do it. Let's see. Yeah, so identifying an acid, it will say acid. Identifying a base, it will probably have some form of nitrogen in it. So it might be an amide, an amide, an aniline, something like that. And then your neutral will probably be like a carbon chain, maybe an alcohol or something like that. Okay. Any other questions with the extraction?
I have a question about it.
Yeah, Everett, what's up?
Are we always going to remove the acid before the base, or could we also remove the base first by adding an acid? Like, does that order matter at all?
The order does not matter. So this question could have been worded differently. And if it was worded differently, we would pull the base out first. But I will say on the test, there's only one correct way that it will do it based on the wording. So I would guess that it will give you what it adds, and you're going to have to identify which one comes out, if that makes sense. It's not going to just say add blank and isolate blank because you could do it either way, and that wouldn't be fair. So order doesn't matter. You just, based on what you add is what you're going to pull out first. So in this one, we added base, we pull out acid. If I rewrote the question, we could add acid and pull out our base first. It doesn't matter. You just have to pay attention to what I'm adding, and that will tell you what you extract. Does that answer your question?
Yeah, thank you so much.
Absolutely. I will say your neutral is almost always last because it just is chilling in the organic layer. And so you have to get everything else out of the organic layer first before you can isolate your neutral. But it doesn't matter which way you do it. Just make sure that you're reading and using context clues to tell you how it will work. Because like, for example, in this practice problem, I stole this from my TA when I took it. You know that you're pulling out acid because you're adding base. Like there's no other blank or there's no other option that I could put in that blank because of how it's written. So just really make sure that when you're doing the test question, you're reading it through and it makes sense at the end when you go through it. Okay, any other questions? This is a tricky question. I know a lot of people miss it, so that's why I'm spending a lot of time on it.
I have a question.
Yeah, Josh, what's up?
How do you know if it's going to be diethyl ether or methylene chloride?
That is a great question. You're gonna end up with a word bank and it's only gonna have one of the options. So as like my word bank here, I have methanol, ethyl ether, and acetone. It's gonna be really similar, but it's only gonna have one or the other. You're never gonna have to decide between them. So just look for the organic solvents, like the ones we've used. So either look for ethyl ether or dichloromethane, okay? Don't use methanol and don't use acetone. We use acetone to clean in this class. Don't use acetone in your extraction, please. Does that make sense, Josh? Any other questions?
Yeah, thanks.
So you
Yeah,
said
for
don't
sure.
ever use methanol for anything?
In the extraction, you won't have to use meth. Did we ever use methanol in an extraction, Colton?
No.
No, we did not. I'm trying to help you out a little bit. So just use the things that you recognize. Um, if we are using an organic solvent, it's going to be the big two. It's going to be diethyl ether or methylene chloride, and the word bank will only give you one of them. So whichever one you are provided, then you need to determine where's my aqueous layer and where's my organic layer, and you're going to do that based on density, okay? We never used methanol or acetone in an extraction, so honestly, I can't even tell you if it's more or less dense than water. So that's maybe a good point. Like, so say I'm working through it and I get confused and I put in acetone because I forgot that Macy told me not to. And then I get to this J blank right here and I'm like, wait, is it the top or the bottom layer? I don't know because I don't know the density of acetone. Got to go back and rework it. Okay, does that make sense?
Totally.
Yes? Okay. I believe in you guys. You can totally do this. Um, if you struggle with this, feel free to reach out to your TAs and be like, can I work through a problem with you? Because I'm really worried about the extraction one. Most of the TAs will be totally chill with that. If they're not, email me and I'll do it with you. Okay. Any other questions with the extraction? Cool. I believe in you guys. Don't overthink it. Just make sure that you read it and it makes sense. Coolio. Leaderboard. Porter still has a great streak. Good job, Porter. Everett's also doing, oh, we got confetti. That's so exciting. Okay. We're now going to do a percent yield question. This is the last question that I have, like the last concept that I have in the review. So if you feel confident about percent yield, feel free to go about your day and do whatever else you have to do today. But if you're worried about percent yield, I'm going to walk through this problem. So dealer's choice. Really fast before everyone leaves. I think people already left because I told them they could. Remember that the test is online, it's on Learning Suite, it's open during finals, it's not open internet, but it is open note. And it is proctored through Learning Suite, so we can access your pictures and it does alert us when you leave the tab. But if you have notes on an iPad, that is okay. Yeah, if you have any questions, reach out to your TA. Okay, cool. We're going percent yield. Cool, yeah. Okay. So when I'm looking at percent yield, I'm going to just read the question really quick. It says, determine the percent yield of dibenzyl acetone for the following unbalanced reaction using the data provided. Record your answer using the second significant figure from your answer. For example, 34.5 would be marked as 4. A lot of people miss this question because they just fill out the answers wrong. This is a format that's because it used to be in the testing center and you would have to like actually like physically bubble on your sheet like 1, 2, 3, 4, 5, 6, 7 or whatever number it was. I don't know why we haven't changed it because it's in Learning Suite. Alas, that's how it is, so we're accepting it, but just remember the format. So if it's 34.5, 4 is what I'm going to bubble, and I'm not going to round, okay? So even if it was 34.9, I'm not rounding to 35, it's staying as it is, it's going to be 34, so I'm going to bubble a 4, okay? Do you guys want to try to work through this, or do you want me to walk through how I worked through it? What would be most helpful for the people who are left?
Just walk it through.
Walk it through? Okay, coolio. So, when I look at these, the first thing I do is I want to double check that it's a balanced reaction. So something that I like to do is look at it visually. So if I look at my product, I can see that I have 2 benzene rings, and 1 ketone. And if I look at my reagents, I can see that I only have 1 benzene ring over here. And so I know that it's probably going to be a 2 to 1 to 1 ratio. And I just balanced that visually, right? I would double check that it is a balanced equation because it's definitely going to change your math if it's not. Okay, so that's the first thing that I do. The second thing that I do is I'm going to calculate the theoretical yield, or I'm sorry, that's a lie. The second thing that I do is I'm going to find which is the limiting reagent. And then once I've found which is the limiting reagent, I'm going to find the theoretical yield. And then we're going to do the lovely actual over theoretical percent thingy. You're welcome, Carson. Okay. Coolio. So I worked this through. I'm so sorry. I don't have pretty girl handwriting, so you're gonna have to look at my chicken scratch. But hopefully you can read it. I tried to color code it so it was a little bit easier to follow. So I'm gonna find the limiting reagent. So back here, I have all of the values that I should need. So I have the molecular weight, the density, and how much I used for both of my reagents. And then for my product, I have how much I isolated. I don't know why it says use there. We're ignoring that. Again, I stole these from another TA, so ignore any mistakes. They're not me. Okay, so benzaldehyde, I used 240 microliters. So the first thing I did was flipped it into milliliters because my density was in grams per milliliter. So then my microliters cancel out. I go to milliliters, and then I'm going to use my density, which is over here, to go from milliliters into grams. So now I'm in grams. And then I'm going to use my molecular weight to go from grams into moles. Okay. So if I'm looking at this like stoichiometric, what is this called? I don't know. It has a cool name, but I forgot it. If I look at all these fractions together, my units are going to cancel out, right? So my microliters cancel out, my milliliters cancel out, and then my grams cancel out. So I end in moles. I always find the limiting reagent in moles because it's a standard that I can compare, right? Moles of benzaldehyde is comparable to moles of acetone. I can't do that with grams. So just make sure you flip it into moles. Okay, so I did the same thing with acetone. I used 90 microliters. And so my microliters cancel out, my milliliters cancel out, my grams cancel out, and I'm left with moles, right? So this is just a conversion factor. This is my density, and then this is my molecular weight, okay? So it'd be really easy to look right here and be like, oh, acetone is my limiting reagent because it is a smaller number than benzaldehyde. You would be wrong, and it really sucks, but you would be because we need to balance it, right? So we have to remember the ratios. And so my benzaldehyde, I use 2 moles of for every 1 mole of acetone. So I need to divide this number that I found here, 0.0023518 by 2 to get my, like the ratio, right? So then I end up with 0.0011759, which is in fact smaller than my moles of acetone. So that tells me that benzaldehyde is my limiting reagent. Okay, does anyone have any questions with that step? Cool. I'm gonna move on. If you have questions, let me know, because this is an important concept. You need to be able to do it, right? Oh, cool. So, found the limiting reagent, coolio. Now what do? We're gonna go to percent or to theoretical yield. So if we go back here, we remember that my ratio is 2 to 1 to 1. So what I did was I took my moles of benzaldehyde and I labeled that as R because I didn't want to write out the whole name. And dibenzyl acetone is my product and that's labeled as P and it's blue because I also did not want to write that out because I am lazy. So I took my moles here that I calculated here. So my original moles, I have not divided it by 2 yet. That is the number that I'm using, okay? So 0.00235518 moles, okay? Then I'm using my ratio that I had, right? 2 moles of reactant of benzaldehyde to 1 mole of dibenzyl acetone. So it's my 2 to 1 ratio. That's why it's really important that we balance stuff. And then I'm using my molecular weight from my product, which is going to cancel out my moles of product and give me grams of product. And then I just did this extra conversion factor at the end here because the problem gave me my actual yield in milligrams. And so I just changed it so it'd be the same unit. Okay. Does anyone have any questions about finding the theoretical yield? Cool. And then I'm going to take my percent, I'm going to find my percent yield, right? So that's actual over theoretical. So in my problem, it gave me 250 milligrams. I calculated that my theoretical yield was 27 or 275.52 milligrams. So that's going to go on my bottom here. And make sure that when you're comparing percent yield that you're comparing apples to apples again, right? I want to compare the same thing to the same thing. So if you want to compare milligrams to milligrams, that's great. Grams to grams, that's great. Moles to moles, that's great. Do not compare milligrams to moles, grams to milligrams. That's not going to work out. You will get the wrong math. So just make sure that top and bottom, we have the same units, okay? And then I'm going to multiply that by 100 and I will get my percent yield. My percent yield is 90.74%. Okay, this is a little tricky, but I had to bubble it on my test. What is my second significant figure? My second significant figure in this case is actually 0. So if a 0 is leading, it's not significant. So if I was looking up here at this benzaldehyde molar number, my second significant figure is actually 3, right? Because these zeros don't count. But here, because my 0 is in the middle, it does count. Okay, so I don't think the test is 0, but just know second significant figure counting in, it's 0, so I'd bubble 0. Does anyone have any questions about how I calculate my percent yield, the process that I used, any of the conversions that I did? Nope. Okay, cool. I believe in you guys. You've been practicing it a lot. How do you feel about the test? Answer if you want to. If not, that's okay. You guys are gonna do great. I know that the midterm was a little bit humbling for some people. It's a little bit harder. The final, you'll do fine on. If you've been in class, you've been paying attention, if you went to a review, you'll be great. If you're stressed about it, I'd recommend going to another review. There are lots of them. Look at the Google Doc. Need more revelation. Fast in prayer, my guy. God really does help. I believe in you guys. You can totally do it. If you're concerned about it, reach out to your TA, reach out to me. We really want to help you. And then make sure you get all your lab reports in because you do need all your lab reports in if you want to pass the class. So just so you know. Does anyone have any final questions before we log off? Whoever said, can we go over my midterm? If you're in my section, I can access your midterm, but if you're not in section 2, I cannot access it. So I don't know who that was, but let me know. It's Josh. Okay, sure. We can go over your midterm, Josh. Okay, anyone else? Any questions before we log off?